Fanglang. Oh, that's so bad. All right, so now it all makes sense. Ho, 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 and happy holidays to whoever celebrates. It's just 1 week till the new year, and I have a few days off, so figured why not do something new. And this time around, I decided to write a compiler backend for a small functional language and do it using F# and .NET. First of all, writing compilers is probably fun. At least it's definitely challenging and a good learning opportunity. So F# seems like a fun language to use and to learn. I haven't used it before, so we'll have to learn as I go. And also .NET is not something that I have worked with. I actually didn't pay much attention to the Microsoft stack for a while, but I was recently surprised that the .NET 6 SDK actually works on Windows, on Linux, and on Mac OS, including native support for M1 CPUs. So it's truly cross-platform. So I figured it would be interesting to also try it out as well. So anyhow, if writing a compiler backend in F# sounds like fun to you, keep watching. All right, so doing a whole compiler in just one video is probably going to be too much. So we need to split it and we need a plan of attack. Let's switch to the whiteboard and kind of draft it out. Okay. So first of all, the name of the language is Fang, from functional language. And the plan is to make it like a variation of the untyped lambda-calculus. Okay. I will talk more about what this means. So first of all, when we talk about compilers, there's usually, well, several parts, at least two. There's the front end. That's usually the thing that does kind of parsing of the source code and semantic analysis. And then there's the backend. The result of the front end is some internal representation. This internal representation can be an abstract syntax tree or AST, or it can be something a little bit lower level, right? And so this IR is passed to the backend, and the job of the backend is to take this internal representation and either execute it, and this is something that we call an interpretation, right? So an interpreter, or it can generate either a bytecode that can be then executed by the VM for the language, or it can be, let's actually write down here. So it's either an interpreter, it can be a bytecode generation, or it can be a native machine code generation. So the idea, at least for now, is to skip the front end altogether for the language and just define the AST by hand so that we can jump straight to the backend. And then we start with the interpreter because that's kind of the easiest thing that we can do, right? Write an interpreter. And here we can do two things. So the first version is gonna be the simplest possible kind of reduction of expressions using substitution. The second version will be something slightly more complex, but also more performant. So let's write this down. So there's going to be a simple and more complex. So when we're done with these two, we can probably proceed to the bytecode generation. And then if I have time and patience, probably I will also tackle the native code gen by producing LLVM IR and leveraging LLVM to do the actual code gen. All right, and so the plan for this video is to define the AST for the language and then implement a simple interpreter that uses substitution. Cool, so let's jump to the code. So this is an empty project that was generated using .NET CLI with this command. And it's actually pretty dope that they have this kind of templating as part of the .NET CLI that is distributed, as part of the SDK. So it's really easy to get up and running, with F#. So as for the IDE, there are several options. So there is obviously Visual Studio, and it's free, it works fine. There is the JetBrains' Rider IDE. It's pretty cool. It's a paid option though. And there's also a VS Code, and I think it's Ionide, the Ionide extension. And I didn't actually have much luck with VS Code and Ionide. It didn't work for me neither on my MacBook nor on this Windows 11 PC. So I'm just gonna stick with Rider. Cool, so let's first make sure that we can build the project. Okay, cool, and it builds, and that we can run the project. Hello, F#. All right, that's cool. So let's also maybe just define a module. And now let's proceed to the actual language definition and the AST. So we need to add a new source file. Let's call it lang. Fanglang. And let's see that things still build. Oh, that's all right. So that's a bit weird. There's one confusing part actually about the project setup. The order of the files actually matters because if it's so let's say if we try to actually define something here, let's say we have another module with examples, and as part of this module we have I don't know, like some const1, which is just an integer 1, and we try to use it here. Hello, F#. Value is, and we'll make it an interpolated string, and so here it will be lang x const1. So it is not happy, right? Although we have this thing, the compiler is not happy. Let's try to build it. Nope, not defined. So what if we do this? I am about to move. Okay, so Rider is still not happy. Wonder why. What do you mean it's not defined? Oh, that's so bad. That's so bad. So the new source file was added, but it was not actually added to the project definition. Rider, this is not cool. Okay, let's go back. Oh, still not happy. What do you need? Okay, so it actually builds fine, and it and it runs just fine. Sure. So let's try to. Have you tried to turn it off and on again? Let's do this. Cool. So now Rider is happy and we can build stuff. So let's actually proceed to the the language definition. Cool. So the untyped lambda-calculus. The untyped lambda-calculus has 3 types of terms, or 3 types of expressions. Type 1 is just a variable, like x or y. Type 2 is the lambda abstraction. So it's basically something like we abstract over the variable x, and the result will be something like x plus 1. That is, if we actually had plus as part of the lambda calculus. But let's assume that we do have these types of terms. And finally, there is the application. And this is where we just take 2 terms and apply one to the other. So we have the expression part of the term, something like this. And then we have the argument part, and it can be, let's say, just y or whatever. Cool. So let's just define this. We have the variable of variable name, and let's say a variable name is just a string, and that's it for now. That's gonna be fine. So then we have the abstraction. So here we have the variable name, like the name of the bound variable. And we have the body, which is just another expression. And finally, we have the application, where we have the expression part and the argument part. So this is actually the vanilla definition of untyped lambda calculus. But as we see, we don't actually have any numbers here, and neither strings. We don't have any operations like addition and subtraction. The thing is, in the lambda calculus, we can actually encode the numbers using church encoding, the booleans and the operations like addition, multiplication, and whatnot. But the encoding is very, let's say, it's not super straightforward, and it's definitely not fun to work with. So we are going to augment this language with literals, with built-in operations like addition, subtraction, comparison, and also let's add a conditional expression here. So first we have a literal of some built-in type. Let's call this b type, and then define b type here as, just let's say for now we have only an integer. Then we have the built-in function. And then we need to define what this built-in function is actually is, and we need 2 types of built-in functions. First, it's gonna be arithmetic of, so the function is arithmetic function, and then we have 2 operands. Let's call it operand A and operand B. And then we also have comparison. And then we have the left-hand side and the right-hand side. Cool. And as we see, Rider is still not happy. So let's double check that it's the compiler is also not happy and not just the Rider. Yeah, that's right. And the thing is, in F#, like in OCaml, to use something, you need to define it first. And here we have the mutually recursive type definitions. So we cannot just reorder them to make everything work. So for this, we need to use another thing called end. And end is created exactly for these types of situations when you have mutually recursive types and you need to kind of make things work. All right, so what is missing right now is the arithmetic function, which can be addition, subtraction, multiplication, and division. And we also need a comparison function, which can be less, equal, or greater. And I actually don't like this name, so let's try to rename it. Cool. So I think that's, oh, so the condition, that's another thing. And here we have the predicate, we have true branch, and we have false branch. All right, I think now this is complete. So let's test it out. Let's use these types to actually define some terms or expressions of the untyped lambda-calculus. So first of all, let's create a helper function to create literal. And this is going to be a literal of built-in type. And let's see if this actually works. What if we go here and make it a literal of 42, and then how do you run? Shift F10. Okay. All right, cool. So it works. Now let's define the lambda expression for the increment. And it's going to be an abstraction term. The bound variable name is going to be, let's say, x. Let's actually do it like this, using named parameters. And the body will be it's going to be a built-in of arithmetic that is add here, and the first expression is gonna be a variable x, and the second expression is gonna be a literal one. Cool. And now let's define another function that will create an application expression that will apply this increment function to some number, some literal. So this is going to be an apply node. So the expression is going to be increment function, and the argument is gonna be literal n. So let's see how this AST actually looks like. So we take cool. So we have an application of abstraction, blah blah blah. So looks good. I think at this point we are ready to proceed to the evaluation part. I'm gonna grab some coffee and get back in a sec. All right, so let's proceed with the evaluation. To evaluate an expression, we need to define a function that will take an expression as an input and return something, right? The question is what it will return. So since we're dealing with untyped lambda-calculus, there will be some terms that will not be reducible to anything meaningful. Let's say we have an application term where the expression is just literal one and the argument is a lambda, like an ID function. So this lambda term is not reducible, and so in this situation, when we encounter these types of terms, we need to raise an error. So we can either express this possibility as part of the result type, so we have either an expression or some form of an error, or we can raise an exception. And here I will actually use exceptions because like these malformed terms is a very sad path for us. And if we like using exceptions to handle these situations, will actually simplify code quite a bit, and will allow us to focus on the meaningful evaluation part. So let's define the evaluation error, and let's say it's string. We can refine it later on if we need to. And then we define the exception. Cool. So now we say that the result of the eval function is just another exception that is reduced as far as we could, right? And so right now we need to match on the expression and kind of handle all the possible cases. I guess the easiest one to handle is the literal. So if we have a literal of built-in type int, we can just return it because we cannot reduce it any further, right? Actually, probably any literal. And interestingly, this pattern match is not complete, but it is not an error. It's by default a warning, and I think this is not the best approach. So let's actually make this warning an error by providing a compiler flag. So, and I know that this exact warning has the code fs0025. So if we go back to the lang, we see that this is actually an error, so the code will not compile. Cool, that's fine. So we have handled literals. Now let's handle, let's say, built-ins. Why not? So here we can have an arithmetic. Come on. All right, so we have the arithmetic function, we have two operands. So let's eval both operands, right? So it's value A is gonna be eval operand A, value B is gonna be eval operand B, and this is actually an expression. And what we need is wait, we need to make this function recursive. All right, now it's fine. So the type of val A and val B are expressions, and we need these expressions to be integer literals. So let's create a function as int, let's say, and it will take I'm always confused by this syntax. So if we have a literal of built-in type int, we just return it. If we have something else, we actually need to raise an error. And the error is actually wrong type. So let's make it not a string, but a discriminated union, or also it's also known as sum type. And so here we will have an expression, and we will have expected type, which is gonna be just a string. So we will raise a wrong type exception, and the expected type is int. What's going on? Yeah. Cool. So now we can actually pipe these values into expression as int. And voila, we have two integers that we can then either add or subtract or whatever. So let's define another function. So we have built in arithmetic fn. All right. And so now we can return a literal expression of an int type with the value. Cool. So this is done. Let's do a similar thing for the comparison. Come on. No. All right, so it's gonna be very, very similar to the arithmetic. We also evaluate two operands. We can probably actually even can shadow the values. Then we need to write another function. And so here I use 1 as a true value and 0 as a false value. All right, and so then we return another integer. Okay, so far so good. So now we need to handle, so I would probably handle abstraction and variable the last. So we have literals, we have built-ins. Let's handle conditional next. So here the semantics is pretty straightforward. We evaluate the predicate. We expect the result of the we expect predicate to be of the integer type. So again, like 0 is false, non-zero is true, whatever. So again, we just do it like this. And then if we evaluate true branch, else we evaluate false branch. So this is all pretty straightforward now. What's wrong? All right, yeah. All right. So what do we have next? Conditional, built-in, literal, application. Let's do well, maybe. Actually, no. Let's do the abstraction first. So let's match the abstraction. Apps, var name, var body. So there are, I guess, a couple ways to evaluate an abstraction. Option 1, would be to try to reduce the body as much as we can. So evaluate the body and then replace this abstraction with another abstraction with a simplified or reduced or evaluated body, right? So reduce the body, return simplified abstraction. Another option would be to just return this abstraction as is. And depending on whichever we choose, we will have a little bit different evaluation strategy. Some will reduce the term to, let's say, a weak head normal form. Some will be fully normalizing, and so on and so forth. For our case, I would say let's just return the lambda as is. That would be all right. And then we can revisit this later if we need to. Now to the application. For the application, we have the expression and the argument. So let's first evaluate the expression. And we know that this expression has to be an abstraction in order to apply to an argument. So let's define this function first. So if it's an abstraction, var and body, we just return a tuple of var and body. Otherwise, we raise a wrong type exception. Cool. So that should be it. And now the important part is actually applying the lambda to an argument. So how do we do it? There are, again, like many approaches, but we will choose the simplest one for now. And basically, it means that we will just look at the lambda body, which is an expression, and we will replace all the free occurrences of lambda var inside lambda body with an argument, which means that if inside lambda body, so if we have the expressions such as x plus 1, we will have lambda var equal to x and lambda body equal to x plus 1. So the free occurrence of x inside the body is the bound occurrence of x inside the original expression. So by substituting free occurrences of x inside the body with the argument expression, we will do basically the reduction of this term. So we will need another function called substitute. Substitute, let's call it subst, where we replace a lambda var for argument inside lambda body. And this is actually kind of the main part of this interpreter, the substitution function. So let's define it here. So we have the var, we have replace for, and we have the original expression. Cool. So if we have a literal, we just return it as is. There is nothing to replace inside the literal. If we have a built-in, so now we will have a lot of sort of mechanical work to, again, like match on all the types of expressions that we need to use in substitution. And we will use the same kind of pattern everywhere, where we call the substitution recursively on the subparts of the expression. So let's define a helper function and call it substfn, which is gonna be a subst var and replace for. So here we need to return another built-in of arithmetic, and here we substitute inside operand A and we substitute inside operand B. All right, we will do the same for comparison. Cool. What's next? Conditional. Same stuff. So let's do the application next. We basically substitute again inside the expression and inside the argument. And now the interesting bits. So let's do the variable next. So if we have the bound name equal to the, let's rename this for simplicity, let's rename this to replace what, or at least for clarity. So if the bound name is equal to replace what, then all the further occurrences of this variable inside, wait, sorry, I'm confused. So if the bound name is equal to replace what, then we just replace it with the replace for expression. Else, we again return it as is. Cool. Now the final case is the abstraction. So here, if we need the same kind of check, So if bound name is equal to replace what, then inside the body, all the occurrences of replace what variable actually mean a different thing. All these occurrences are bounded by this lambda abstraction, so we don't need to go deeper and replace them. So we just return expression as is. Otherwise, we again proceed and we return the same abstraction, but with substituted body. So substitution is done. So if we go down, we will see that everything's fine and we're just missing one case. Incomplete pattern matches on this expression. All right, so if we match on variable, then again, like we have a couple choices how to evaluate a variable. If we encounter a variable during the evaluation function, what it means is that this variable is not bounded by any lambda. So it's a free occurrence of a variable with no value. So we can either return it as is, or we can raise an exception and say that this name is not bounded to anything, blah, blah, blah. So that's depending on what we do with the variable. We may or may not have the option to use either option 1 or option 2 of the abstraction evaluation. But anyhow, let's just return the expression as is. Don't do anything with the lambda, sorry, with the variable. Just leave it as is. And I think this actually finalizes the evaluation function for the expressions. Right, so that's not so bad. It may not work, but let's see. Let's actually run the program. So what we have here is the incur app of 42, and what we would expect from the evaluation. So what we would expect is a literal 43 as a result. So let's see whether it works or not. No, for some reason it didn't work. I wonder why. So let's see. Let's see what we are missing here. So I would expect this to actually go into the built-in branch and just, do the thing. But I guess the nice thing about F# is that you actually have a very nice debugger and you can debug the thing. So let's do it. All right, so we need to replace x for variable x for 42 inside var x expression. So that should be pretty straightforward now. All right. So what's the result? Okay, so the substitution was performed correctly. We have a built-in of arithmetic, of add, of 42 and 1. Let's see what happens next. All right, so now it all makes sense. It's not just the substitution that we need to do, we also need to evaluate the result. So that's what we forgot here. So let's pipe it into eval once more. Let's run again. All right, so the value is 43. That's cool. Let's maybe try something different. So let's say we have the add function. So basically, let's simulate the addition of two integers using some lambdas and applications. So we need the first abstraction with a variable x and a body equal to another abstraction with variable y and a body equal to built-in arithmetic. Let's actually make it a subtract sub. And so here we have var x, var y. Cool. And so now let's define another expression. That will apply add function to x and another apply to y. So this is a little bit more complicated, right? So we have the nested lambdas, we have nested applications. So let's see if this actually works. We probably don't need this anymore. Okay. So this needs to be renamed. So we would expect 40 as a result. Let's see how it goes. All right, so far so good. So I guess at this point we have a pretty good confidence that this evaluator works. So it's time for the ultimate test for this sort of application of function and substitution. And this is the Fibonacci function. The usual way to define a Fibonacci function is something like this. And this is a recursive definition. The problem is that in our language, there is no way to kind of bind the name to something or recursively bind the name to something. And so we need to use a workaround. And this workaround is called a Y combinator or also a Fixpoint combinator. And this is a way to actually emulate recursion in the lambda-calculus. So there are actually several definitions of the Fixpoint combinator. One of them is suitable for lazy languages, and the other one for eager languages in terms of the evaluation strategy. And we will see in a moment what that means using just our evaluation function. But first, let's define the lazy fix point. And this is, I mean, definition is, I just cannot internalize it. So I'll just copy it here, and then we define the AST for this combinator. So let's start with the inner part first. Let's call it inner abs, and it's the abstraction with variable x, and then we have the application where the expression is variable f, and the body is another application with an expression being variable x and the argument being variable x. Whew. And you can probably already see why this definition is suitable only for lazy languages. And this is because of this part here. So we apply x to x. In an eager language, it will just basically recurse forever. But let's continue. We need another application abstraction. And this abstraction has a variable f, and a body is the application where the expression is inner abstraction and the argument is inner abstraction. All right, so that's the lazy fix point. Now let's define the Fibonacci step. And this is gonna be a function that takes two parameters. It takes, let me just write it down here. So it takes itself, and it takes the number that we want to calculate the Fibonacci number for. And then it's kind of the usual thing, right? It's a conditional. So let's write this down. We have the abstraction. Its body is another abstraction. Its body is a conditional. So the predicate, oh, that's going to be very convoluted, but bear with me. Whew. Yeah, that's pretty confusing. It would be nice to have a front end to kind of define these ASTs with less hassle, but we have what we have. That's fine for our cause. So let's see what would be the Fibonacci function of n, where n is the integer. So first of all, we apply the fix point to the fib step to get the Fibonacci function. Basically, that's the apply node, where we use lazy fix point and the fib step. And then we apply the function to literal n. Now, let's see how and whether it works. Let's start with the Fibonacci of 1. Okay. This was interesting. How about T? Okay, how about 3? All right, not bad at all. So it looks like it works. I guess it's gonna be interesting to let's define a new function. Okay, so let's remove this. Let's define this. It'll take an expression. Then it will evaluate it. And then it will output the result. All right, so we spent about 200 milliseconds to evaluate the Fibonacci of 5. Well, I guess it's it's not too bad. Let's see whether we can do Fibonacci, like the 10th Fibonacci number. All right. How about 15? How about 20? How about 26? Okay, so basically I guess maybe we could do 30 as well, but it's probably gonna take a long time. But still, it's like the Fibonacci of 26 takes 1.7 seconds, and Fibonacci of 30 takes 12 seconds. Well, I mean, for a very naive evaluation of lambda-calculus, that is about 100 lines, you know, from start to finish. That's not too bad, not too bad at all. Now, let's get back to this point about lazy evaluation and eager evaluation, and see where this actually matters. So if we go back to the application node, we see that we take the expression, we evaluate the expression, and then we substitute the variable for the argument, unevaluated argument. So this is basically kind of a call by name evaluation strategy. So we defer evaluating the argument until we actually need to. So let's say what will happen if we change this a little bit and we evaluate the argument first before trying to evaluate, trying to substitute it. So let's do this. And then we replace for eval. Maybe just call it. So if we just run this thing as is, it will actually lock up. Probably on the first call to Fibonacci. So we can see it here. Yep. So it's not a lockup, but rather a Stack Overflow. Yeah. So we evaluate the applications. That's totally fine, but then we fail with the Stack Overflow, simply because, as I said in the example here, we have this application of x to x, and this is just not gonna work. So we need a different Fixpoint operator, and let's define it here, and let's call it eager Fixpoint. So here's the definition of the eager Fixpoint operator. As you can see, the difference is the argument to f, which now uses an indirection via another lambda abstraction. So let's do it. Let's define it here. So we copy this thing. So let's define this abstraction that uses variable v to define the application of variable x. Actually, it's application of variable x to variable v. And then we will use this indirection instead of the argument here. So if we go to the Fibonacci definition then and replace this with the eager Fixpoint and run the program again, let's see if it works. All right. Yes, it does. Interestingly, it seems to work slower. Yeah, it seems to work a bit slower, but anyhow, this was not supposed to be the fastest interpreter ever. But I think it's a very nice way to kind of illustrate what the lazy evaluation strategy means and what the eager evaluation strategy means, and that the difference is actually not very huge. All right, so I think at this point we can consider this evaluation function complete. It can do simple things like defining function, applying functions, applying some built-in operators like addition and subtraction, and also not so simple things, as we have seen with the Fixpoint combinator and the Fibonacci function defined using this Fixpoint combinator. So far looks good to me. So if we go back to this whiteboard, we can probably mark the simple interpreter part as done. So for the next video, I will implement something a little bit more sophisticated, probably an order of magnitude more performant than the simple interpreter, but not much more complex in terms of the implementation code. It will still be a tree walking interpreter. And so for the one after that, I will implement actually a bytecode compilation strategy for the lambda-calculus, which means we will need to define sort of the bytecode, the instructions and opcodes, right? And also we will need to implement a virtual machine to actually run these opcodes. So this is going to be a lot of fun. So yeah, that's it. Hope it was helpful, and thank you for watching. See you next time. Peace.